Hello, we are Ian Palabasan and Mhoanna Besonaya from 11 Galileo Galilei with our short video project for basic calculus. Today's lesson shall be determining whether or not functions are continuous at a certain point. Normally, a function will accept a value, say x, and output a result, say y. A function is said to be continuous at a point if at that point in the graph of the function the graph is mostly, well, continuous, which we can easily discern visually. How can we say that in mathematical terms, however? Here we have an example function. F of x is equals to x squared plus 2x plus 1 divided by x minus 1. If we set x is equals to 5, we get y is equals to 6. If we get x is equals to 4, we get y is equals to 5. If we set x is equals to 3, y is equals to 4. If x equals 2, y equals 3. Judging by this pattern, you would assume that x equals 1 will yield y equals 2. But division by 0 is not allowed, so we get a null answer. As x is equal to 0 yields y is equals to 1, and x equals negative 1 yields y equals 0, it is clear that this function only breaks down when x is equals to 1. Now let's look at the graph of this function. It pretty much looks like the graph of y is equals to x plus 1, as if we tried cancelling factors out from our original function, this is in fact what you would get. However, we have a hole where x is equals to 1 is. We could thus say that this function is discontinuous at x is equals to 1 and continuous elsewhere. So the first criteria for a function to be continuous at a point is thus that the function must have a result at that point. Why don't we look at another function then? F of x is equals to x plus 1 if x is less than 0 and x minus 1 if x is greater than or equal to 0. Let's try what we did earlier. If x is equals to 3, we get y equals 2. If we get x equals 2, we get y equals 1. If we get x equals 1, we get y equals 0. If we get x equals 0, we get y equals negative 1. If x equals negative 1, we get y equals 0. If we get x is equals to negative 2, we get y equals negative 1. It seems like this function is continuous at all points, as each x value we give it as a result, right? Let's look at its graph. At x equals 0, we can see that the graph has a sudden jump. Even though the function does give out a result when x is equals to 0, this function is discontinuous at this point, as there is a sudden break or jump in the graph. How would we specify this mathematically though? We could use the concept of the limit of a function f of x at a point a, which is the value that f of x approaches as x approaches a. On a graph, we can find this by following the graph to the point a. In this function's case, if we follow the graph from the right, we get a value or a limit of y is equals to negative 1 from the right hand side. If we follow it from the left, we get y equals 1. As the two values are completely different, we can say that this graph does not have a limit at that point. The second criteria for a function to be continuous at a point is thus that the function must have a limit at that point. And let's look at another example. So f of x is equals to x plus 1 if x is not equal to 0 and x if x is equals to 0. Let's see if this function is continuous at x is equals to 0. Looking at the graph, we can see that the function satisfies our first criteria, giving out y is equals to 0 at x is equals to 0. It also satisfies our second criteria, it having a limit of 1 as x approaches 0. However, from the graph, we can clearly see that the function is discontinuous as the graph suddenly jumps down from 0 to 1 at x is equals to 0 and suddenly jumps back again. In this case, the limit and the result of a function do not match at all. The third criteria we have for a function to be continuous at a point is thus that the limit of the function must match the result of the function at that point. Thus, we have three criteria for determining whether a function is continuous at a point or not. So first, the function must have a result at that point. Second, the function must have a limit at that point. Third, the result and the limit of the function at that point should match.
So here we have a few examples. Try to determine whether the function is continuous at that point or not. Give you a few moments to answer these questions. Please feel free to pause this video until you're done. If you got them all right, why don't you post it down in the comment section below? Feel free to do the same if you have further questions or suggestions in our video. Don't forget to give this video a big thumbs up, then share this, and also subscribe to our channel if you were able to learn something in our video. Thank you very much, and we'll see you on our next video. Bye!
Underneath the palm trees, you can leave your worries. Listen to the